Is it now visible?
Yes.
Okay. Thanks a lot. So first of all, I'm extremely thankful to organizers for giving me this opportunity to share what I have been doing. And at the same time, I congratulate the organizing committee for having such a wonderful program to unify all the astronomers, astrophysicists from different parts of the world on a common forum. At the same time, and different types of heterogeneous audience have been accommodated here. I came to know that even UG, PG children are also attending. Okay, so that's why accordingly, I have prepared my talk in such a way that educative part is also there, and together with applications and our investigation results. So as per that, the title of my presentation is Nucleus Acoustic Waves in Compact Astro Environments. And astro environments, everybody knows as it is your stellar plasmas. So fundamentally, what I'm going to give a brief introduction and about this is brief introduction about our university as well. This is our Tezpur University. This is the entrance gate and different parts, auditorium, etc., etc. So you are most welcome. Okay. So the presentation layout is introduction, then motivation, then physical model, numerical results, main conclusions, and bibliography. Okay. So as you know, everybody knows that there are four states of matter. First of all, the solid state, this is the first state of matter, that is solid, then liquid, then your gaseous, okay, then lastly plasma. This is well known, but only for those who are new in this area, I am talking about that. And in case of plasma, what happens, the amount of energy or heat if you supply, then what happens, the electrons can be taken out, then it becomes ionized. So statistically large number of electrons, ions together, that is what form a new state of matter, that is unique state of matter, that is your plasma. Okay. And typically the density, is it visible? Okay. So for example here, typically we can see that this is the temperature, okay, that is energy more than your ionization potential of hydrogen, then it becomes plasma. So plasma is a statistical collection of coulombic particles together with some neutrals. Okay, so this is history of the term plasma. As you know, this is your plasma in the, it comes out plasma, just your one medical engineer, and plasma, it is named after that moldable substance or formed substance, jelly like substance. Okay, and medical engineer he has first found, and after that in plasma physics, in the actual branch, it has been named after the American Nobel laureate chemist, surface chemistry. He was awarded Nobel Prize in 1932, and he first coined the name plasma in the world of physics. Okay. Okay, fine. And these are some realistic medium, but it has correlation, and henceforth it has been named as plasma. Okay, so plasma as a whole, what I have told you, that it is statistically, just one point is that it is statistically a large number of particles. Okay, so here we can see that large number of free electrons, ions together, this alongside neutral, it contain what is called plasma. So plasma is the unique state of matter. Okay, but at the same time, one controversial definition is also there, that plasma is the first state of matter, because due to the primordial universe, when the universe was formed during Big Bang, radiation and matter remained together, and the matter remained in the form of ionized state. So that's why that is called plasma. But mostly, usually it is called the fourth state of matter instead of the first state of matter. Okay, fine. And what is the unique feature of plasma? It is, everybody knows, this is your existence of collective degrees of freedom. Okay, and this collectivism, it is the most important part. Okay, and it appears only because of the Mill field existence inside plasma, unlike neutral gas, where there is no presence of one particle is not affected due to the presence of other, but in case of plasma it happens. And what are the different criteria for plasma existence? One is your length existence, condition for length. So length, as you know, this is your length must be sufficiently large. How much large? Length greater than the Debye length. Then your device sphere, it must be overpopulated, and then your plasma frequency, there is also one more condition, and these are fundamental conditions. Okay, fine. After that, so even in the universe, plasma is everywhere. and 99%, as you see, 99% of the universe is in the plasma state. Okay, so plasma is everywhere. Okay, fine. And the sun earth coupling, that is another. And as you know that this process, the nuclear fusion, with the help of which energy is generated in the sun, that is again, this is the process and by which this energy is coming out. Okay, so this is the process by which energy is coming out in the sun. So this is again plasma, another example. Okay, and what are the different plasma confinement processes or mechanisms available? As plasma temperature is high, so normal material cannot hold it. So therefore, magnetic confinement, inertial confinement, and all other these confinement processes are there. Okay, so magnetic, these are. And tokamak, that is your artificial sun on the earth, that is formed, derived from this Russian word, which means toroidal chamber and magnetic coil. Okay, fine. And it is a device, powerful device to generate plasma energy. Okay, and this is the typical dimension. One jet tokamak is shown. Okay, and this is the ITER. Okay, so ITER everybody knows, this is for energy generation, and it is successfully, it is hoped to be coming out in the year. Okay, in the year of this, it is successfully coming out in this year. Okay, and it is the typical picture. It is under, still under construction, it is going on. Okay, fine. And this is a phase diagram for different materials or different objects in the plasma. Out of that, we can see that this is our sun, solar core. Okay, it appears here in the space defined by number density along this direction and temperature along this direction. Okay, fine. Then there's the one important point of collectivism. This is your device sphere. Means it is plasma that if you apply one external perturbation in the form of charge, whether it is positive or negative, then what happens? Collective dynamics stirs, means opposite polarity charges will come and they will just shield it out. In case of positive, it becomes your negative, and in case of your negative, it becomes just positive. Okay, so due to that, this collective dynamics, what happens? The normal coulombic force, which was your this one, this force, the normal coulombic, this becomes shielded out when the exchange particle, that is photon, is massless. But whereas in the case of device shielded potential, which is given here, this is your coulombic unshielded, whereas this is your just device shielded. But in this case, the mediator photons as if acquire mass, and this is the mass given by this equation. Fine. So in case of plasma, so this difference, the difference between the two, which appears here, it is only because of plasma effect, what we can see. But asymptotically at zero, it becomes the same. Okay. Then this is your normal electrostatic Poisson equation, and this equation has a term, this term, and this term is one scaling factor. Already I have defined scale length, and as per that, if you see, if we have a dimension L just greater than your dy length, then only then it becomes quasi-neutral, else non-existent. So different conditions are given here. As per this, polarization effect must exist at this condition. Okay. Okay, fine. And what are the different formalisms? Formalisms are your, out of that, single orbit, that is only for your dilute, very dilute, and then electromagnetic. Okay. So, and another is your magneto-hydrodynamic, that is also fluid description. And this is your kinetic. This is for individual macroscopic behavior and to study the individuality of particles. But out of that, we'll be using, or most of the astrophysicists use only these two in general. It is available in most of the cases of theoretical astrophysicists. Okay, fine. And it is a one cartoon for children to understand what a wave is. So wave is, as you know, it is a disturbance which can propagate. It is only the characteristic that it is the group velocity which makes oscillation into convert into wave. And this is one typical picture of your oscillation, and accordingly what is the phase portrait, that is also available here. This is the phase portrait. Okay, so this is your in the coordination space, and this is your in the phase space. Fine. Okay, and this is one wave, how wave in normal acoustic wave available in your gas. So it propagates through compression and rarefaction as visualized here in this cartoon. Okay, fine. And this is again transverse wave, how it propagates. This is another cartoon. Okay, fine. So distinction features that wave and oscillation, what is the difference? Already I told you that group velocity max oscillation into wave, or wave without any group velocity becomes just like oscillation. This is the definition I have given, and mind that this oscillation to exist must be there competition between inertia and elasticity. Okay. Okay, fine. So introduction to our one case. So what is the medium where from nucleoacoustic waves are generated? This is your quantum plasma, and for quantum plasma, we have considered quantum degenerate plasma, and this is given here. So your degenerate plasma and your compact astrophysical objects are mostly formed of, and what are these? Bohm potential we are going to again define, and viscoelasticity we have considered, and the origin of nucleus acoustic waves, which is the title, which is already they are in the title itself. Okay, fine. So what happens in case of classical plasma? High temperature and low density. In case of classical plasma, this is your high temperature, low density. Whereas in the case of quantum plasma, the reverse effect. Fine. And condition for existence of quantum plasma is that the number of particles in the device pair must be larger. Okay. And this is overall the pressure, and this is the equation of motion in case of quantum plasma, and this pressure is coming out only because of the overlapping of steps. Okay, fine. Okay, fine. So this is one more correlation parameter, which is called coupling parameter, and it gives whether it is weakly coupled or strongly coupled. Okay. And nucleus acoustic waves, electrons acting as thermal species, whereas nuclei acting as inertial species. So excitation of longitudinal acoustic waves towards energy transport processes via compressions and rarefactions in a periodic fashion. So that is your nucleus acoustic waves. So nuclei are always inertial species. Fine. And compact astrophysical objects, everybody knows these are extreme under extreme conditions. So quantum plasma astrophysically exist in various objects like dwarfs, Jovian planets, etc. And even in laboratory, in the devices, this quantum plasma exists. And again, standard materials as well, these exist. Fine. And intense laser plasma interaction, that is another next generation inertial confinement fusion schemes. Okay. So this is one cycle by which star evolves, and here we can see this is the phase position where from where white dwarfs can be located. Okay, fine. Okay, and this is the same picture but in a different form. Okay, this is a typical picture of white dwarf star. Okay, and around surrounding white dwarf, what we can find, their dust exists here. Dust here again, dust, different dust exists. Okay, so dusty atmosphere, which is again correlated. Correlated means strongly coupled. Okay, then again, these are differences fundamentally between quantum plasma and classical plasma. Okay, so one important point is that already what I told you, that density as well as temperature, this is the fundamental difference. The rest of the things are just I have drawn, but fundamentally speaking, this is the main. Okay, then our model of quantum plasma, what we have done, this is the our investigation. So motivation is that there are different types of waves and stability features, but which are yet to be understood, nobody has done. So that's why we have considered one hydrodynamical model and corrected, and these are again corrected with the help of dimensionality as well. And we have used modified equations corrected from all the aspects, uh, and applying that all those equations, I am showing what are those equations, that schematically these are structurally these are different layers, and what are heavy nuclei, these are given here. Heavy nuclei are these are your heavy nuclei, and electrons are also there. Okay, so these are the basic equations. So we have considered spherical geometry, but spherical symmetric geometry, and non-radial, that is your polar and azimuthal parts have been ignored for simplicity. And with that, what we can get, this is your equation of continuity, which is nothing but your density conservation or mass conservation equation, and this is the force balance equation, which is also called momentum equation. Okay, and dynamics of light nuclei, similarly these are inertial species, and we have modeled similarly in the fluid model approximation. Then again, this is for heavy nuclei, but in addition, in the case of heavy nuclei, what we have done two things. One is this is the elastic term, and this is the viscous term we have included in the heavy nuclei only. And these are coupled. Coupling is made with the help of electrostatic Poisson equation and gravitational Poisson equation. That's all. Then this is our standard astrophysical scheme of normalization, and different terms are generic, conventional. and this xi is your radial position. Okay, and time scale has been normalized with this, and rest of the things are done as per the convention. Okay, fine. Then these are the normalized form of the same equations. Again, the same equations. And after that, we have used spherically symmetric radial analysis. So this is the analysis we have done. Okay. So this term coming out only because of spherical symmetry. Okay, fine. So after substitution, we get the linearized form of the equations in the omega k space. That is your Fourier space. Fine. So after method of decoupling and simplification, what we get? The dispersion relation in complex form. Fine. And here different terms are there. And as far as we see here, this is your heavy nuclei term. Okay, and here this is your heavy nucleus term, and this is your light nuclei term, and this is your electronic contribution term. So different contribution constituents have contributed to the resultant wave activity dynamics in this form. Okay, and for simplicity, we have applied one approximation that linearized form of the equation is also considered, and as per that, we get the different terms as follows, and finally it reduces to a new form, the simplified form, which is this, and we just solve this numerically, and these are the different results. What we find that two types of electrons have been considered already. One is your ultra relativistic, and second one is your non-relativistic. So in the ultra relativistic regime, what we can find that this parameter, density parameter beta has already been defined. This is your beta, and beta is already defined. So as per that, it decreases along this direction. Then again, in the non-relativistic regime, these are the lines. So what we can find that phase velocity is sensitively affected due to beta variation, but in the non-relativistic regime rather than in the ultra-relativistic regime. And at the same time, we had found that the growth rate, again, this is increases, means it features stability in the non-relativistic regime, whereas this is your in the ultra-relativistic regime. So what we can conclude that again, the stability, that is your growth, also highly affected, sensitively affected differently in the two different regimes of electronic dynamics from the relativistic point of view we have considered. Then these are the similar profiles, but now for with mu variation, and mu is already given. This is nothing but your again charge density ratio between heavy and light nuclei. Okay, and these are again similar variations for quantum parameter, that is your this h, and we have found again that h assigns phase velocity variation as well as the stability of the nucleus acoustic wave instability in one model. So as per that, in the two regimes, these are affected differently. And another important point is that the as you go at higher k means your, if you move towards the acoustic regime more, then these two all together merge together, almost there is no difference at all. So stability at higher k asymptotically becomes same, almost the same. Higher k means more acoustic regime. Okay, and these are the 3D picture, and along what we can say, we can again find similarly that over xi, here you can see that over xi, okay, for your small k, for small k it becomes almost linear, but for higher k it becomes non-linear. Okay, and again here is the growth, and again we see for this behaves non-linearly here, then again linearly there. So whenever linearly it varies, it assigns, it favors more in the acoustic domain than in the gravitational regime, because in case of gravitational, what we know that this becomes this part is almost non-linear. So a little bit non-linear features are exhibited here, but over k here in this regime it becomes over k, it becomes almost linear. Okay, and this becomes almost non-linear. Okay, so this is just a 3D profile of the same what we have already mentioned before. Okay, regarding the stability features of the instability. Okay, and now what is the nonlinear stability? The same equations, but we have now used reductive perturbation technique, which is also called multiple scaling techniques, and as per that we have used stress coordinates, and these are derived especially for the acoustic wave dispersion relations, and this is one order parameter, scaling parameter, and this powers scale our system. Means we have now switched over to slow coordinates, okay, in order to see weakly nonlinear perturbations. And these are the this is your, as you know, this is your equilibrium, this is your equilibrium, and this is lowest order perturbation, this is next higher order perturbation. And this way we have derived, after method of decoupling and simplification, we derived one your extended EKTB equation. That is your extended EKTB, already I mentioned here, extended EKTB equation on electrostatic potential perturbation, and electrostatic, again the same equation on gravitational potential perturbation. Okay, fine. And right hand side, these are the extended. This can act as source or sink depending on the conditions, parametric features we are assigning to. Okay, so these are the various coefficients over here. And after that, we have just numerically solved the system, and these are the results what we got. So as before, we have just plotted, and as per the profile what we have shown, this is your our frame velocity, our reference frame velocity, and as per that we can find that for different values, it is different. And overall conclusion is that referral frame velocity stabilizes both the electrostatic as well as gravitational fluctuations in our model setup. Similarly, we have also found the features, the variational features of the perturbations with your mu parameter. And as per that, what we can see that with mu, it again acts as minor effects. For this one, for this there is almost no effect, but for this sensitive effect at your higher xi, higher position. So what we can conclude that this electric charge concentration imparts minor effects, okay, on the electrostatic, whereas it stabilizes the gravitational fluctuations. And this is because only because of the complex dynamical gravity electrostatic interplay operating over that. And these are similar profiles of the perturbations. And here again we see that this charge to mass ratio again imparts insignificant effect on the electrostatic, insignificant, whereas sensitive effect on the gravitational fluctuations. Okay, that is destabilizing effect. Okay, and this is overall conclusion what we have drawn, that semi-elliptic model has been constructed to study nucleus acoustic waves in both the regimes, linear as well as non-linear regime. Okay, and non-planar radial wave analysis, that is spherical wave analysis without any contribution considered from polar as well as azimuthal directions. Okay, so that is incorporated, and different stabilizing as well as destabilizing agencies have been explored and investigated. Okay, and these are the different parameters what we have found out. And in the case of electrostatic perturbations, what we find, regular solitine anti-solitone pulse trends as well as gravitational asymptotic your oscillatory solitary features, these are also investigated. And various non-linear stability features we have already found out graphically we have shown. And our, from the application point of view, these results are applicable to find the various wave dynamical processes going on inside compact astrophysical objects and their compact astro environment surrounding that, like what I have shown, that in the case of compared to your white dwarfs, dust particles are there, so there's those various nuclei is also there. So this may be considered, this model can be applied to study the stability of all those environments wherein a strong coupling is there and existence of various nuclei is there. Okay, so this may be existence. And these are some references, and we have also done various different works based on quantum plasma, and the results presented here mostly comes from your this work published in physics of plasma, and another work, the nonlinear part, published in EPL. Okay, so these two combine the results presented here. And of course, this formalism has been already utilized to find out nucleus acoustic wave dynamics in superfluid neutron star. Okay, so that is already completed, but we have not communicated and we have not shown all those results. It is here, I can right now I can show, but I have, due to time constraint, I have not going to show. Okay, so I want to finish it with one quotation. So a person who never made a mistake never tried anything new. This is by Albert Einstein. Okay, and thank you very much for your kind attention.